Yeah, yes, Sanjay, let's start.
Okay, let's start. Okay. All right. Good evening, guys. Welcome you all to IGC. I hope you guys are all doing well. So, this session is going to be a demo session on gas dynamics. So, I'll be just taking you all through a topic, a small topic, and feel free to ask doubts. Okay, so let's make it more interactive. And if you guys have any concerns, anything, please feel free to stop me at any time. Okay, you can put down your comments in the chat, or you can even unmute and ask. Okay, all right. So before we start, let me just introduce myself. My name is Sanjay, and I am associated with IGC since quite some years. And I graduated from IIC in 2024, and my area of specialization was on hypersonic flows or high speed aerodynamics. Yeah, so and I teach aerodynamics, gas dynamics here at IGC. So yeah, that's all about me. Let's get started into the session now. So yes, so we are going to just learn something about gas dynamics. So before we start, let me give you a very quick overview about what the subject all about is. So many of you might be from aero background or from mechanical background. You would have heard about this subject, right? So some of you might already be knowing what it is, but for others who are totally new into this, okay. So what is gas dynamics? So at IGC here, we have something known as aerodynamics module. Okay. So the aerodynamics module, uh, we have split it into few subjects. So one of which is aerodynamics itself. Okay. One of it is aerodynamics, and we also have gas dynamics, and we have basic fluid mechanics. Okay, so basic fluid dynamics or fluid mechanics. Okay, so these are the three subjects or the three courses that we cover under aerodynamics module. Okay, so it's we have clubbed these three subjects into one module because they are somehow related to each other. Okay, and this will help you as you move into other subjects like flight mechanics, propulsion. Okay, so these courses are going to help you there. All right. So what is gas dynamics now? So generally we start gas dynamics after we learn aerodynamics. So when we talk about aerodynamics, we mostly learn about the flow of air or the flow of any fluid past bodies, right? So in aerodynamics, we mostly deal with external flows, okay, where you have a body. It could be a bluff body or it could be a aerodynamically designed body, okay, a body which is designed to produce aerodynamic forces. You have flow past such bodies. We are going to analyze them. That all that comes under aerodynamics. Okay, and what is gas dynamics? So gas dynamics is very similar to aerodynamics. The only difference being we consider that we will be concerned with the flow of a gas, okay, which can change its properties as it flows past bodies or as it flows through the body. Okay, so gas dynamics could be, it is not just confined to external flows. We also have problems which deal with internal flows. Okay, so we will have flow through pipes, flow through ducts, flow over an aerofoil. So all of this could be considered as gas dynamics. Okay, so I can say that aerodynamics is a subset of gas dynamics, where gas dynamics is kind of a superset where we deal with more general sort of problems. Okay, another thing that is going to differentiate aerodynamics and gas dynamics is something known as the compressibility of the fluid. So in aerodynamics, we'll mostly consider the flow to be incompressible, where the density is going to be constant with space and time throughout the flow. Whereas in gas dynamics, we will relax our assumptions. We will consider that the flow is going to be compressible. Okay, so we will start the course itself with something called as compressibility. Okay, so we will deal with compressible flow of gas. So generally, gas dynamics is also called as compressible fluid flow. For the reasons that I told you, we are going to mostly deal with flows which are compressible in nature. So we call them as compressible fluid flow. Alternatively, we also call this subject as high-speed aerodynamics. Okay, so as I told you, in aerodynamics, we will deal with incompressible flows which are of fairly very low speeds. Okay, and contrary to that, we will have high-speed aerodynamics where we'll deal with flows which move very fast. Okay, how fast, that we will see. Okay, we have something to quantify the speed of the flow, which is known as Mach number. We will define different regimes of the flow where the flow is going to be either subsonic, transonic, or supersonic, or hypersonic. Okay, that will classify your aerodynamics into low speed aerodynamics or high speed aerodynamics. Okay, so in gas dynamics, it's mostly going to be high speed aerodynamics. Okay, so if someone tells you that it is compressible fluid flow or high speed aerodynamics, they are referring to gas dynamics. Okay, so these are the different names. Now, talking about the syllabus, uh, we have different topics. So we generally start with thermodynamics. We start with the basics because gas dynamics originates from itself from the thermodynamics. Okay, so we'll start with that. Then we will look at gas properties. Okay, what are the basic properties of gas which dictates the flow through bodies or flow past bodies. Okay, there we will see isentropic relations. This is one of the most important part in gas dynamics. We follow that an ideal process in gas dynamics is considered to be an isentropic process. Okay, so the name itself tells you that the process is going to be of constant entropy. Okay, the entropy will not change throughout the process. And then we will jump to learn something known as shock. Okay, have you all heard about this anytime? Have you all heard about shocks? Yeah, at least aero guys must have heard. Yes, very good. Okay, so what is a shock? A shock is basically a standing discontinuity in the flow. Okay, so you have flow. When the flow properties change very abruptly, suddenly you get a shock wave there. Okay, now it need not be a stationary shock wave. It could also be a moving shock wave. Okay, we will see different examples. So it is we're going to learn about shock waves. So shock waves are, they form the crux of the entire course of gas dynamics, because this is not a hypothetical concept. Okay, it is a real concept, and you get to see them. If you have seen some supersonic aircrafts, you see shock waves forming, right? You see, for example, when an aircraft is crossing the sound barrier, you would see the shock wave and the gas ionizing, right? So at least in movies and all, you would have seen, if not in real. So shock waves are important. We will learn about shock waves. There are different types of shocks. We have normal shock, we have oblique shock, which is at an angle, and opposite of shock is an expansion wave. So shock waves generally compress the flow, expansion waves will expand the flow. Okay, so once we learn about shock waves and expansion waves, we will go through 1D flow through variable area ducts. Okay, so we will learn how does a flow change when it passes through a duct. Okay, so duct flows, it becomes a very important concept. And then in the last module, we will deal with some specific type of 1D duct flows called as Rayleigh flow and Fano flow. So these are again one-dimensional flows, but with heat addition or with friction. Okay, so again we will see how the gas properties change. and what happens when gas properties change inside these ducts or when the flow passes through a body. So this is all about gas dynamics. Okay, so we are going to learn about these things in the entire course, and trust me, it is one of a very interesting subject. Okay, this will help you understand propulsion, the rocket propulsion, turbo machinery. There are a lot of subjects, flight mechanics, a lot of subjects linked with this particular subject. Okay, so yeah, it is that important when it comes to aerospace applications. All right, so but this lecture we are going to focus on one topic. I'll just quickly take you through this topic called as flow through variable area ducts. Okay, so we will understand about variable area ducts. What do you mean by, so what is a duct? A duct is basically a closed pipe or it's a passage to a flow. Okay, when I say variable area duct, the area of this passage changes from one position to other, and there's a flow passing through this duct. We will see what happens to the flow. Okay, so let's get into the session now. All right, when we talk about one-dimensional flow, what does a one-dimensional flow mean? The name itself tells you that the flow is just confined to one dimension. Okay, so if let's take a passage, and if I say a flow is moving through this passage, and if I can just see that the flow properties are uh, just changing in one direction. Okay, the flow is only moving in one direction. There is no change. There is no movement of the flow in other directions. Then we call this as purely one-dimensional flow. And any problem when it is simplified to one-dimensional flow or one-dimensional analysis, it becomes very simple to analyze. And we always start with 1D analysis. Okay, and then we move to 2D or 3D. So that is a one-dimensional flow. Now, in one-dimensional flow itself, you can have flow with constant area duct, okay, or variable area duct. Now, what is a constant area duct? It is a passage or a duct which has constant area. So the area is not going to change. So if let's say this is the inlet area AI, this is going to be the same area everywhere. Okay, so AI is going to be equal to AE. Okay, so the area is not going to change. And what happens? What happens when a flow passes through such ducts with constant area? You will see that the flow is going to, so the flow is going to enter, this is the inlet, and the flow is going to exit through the outlet. Okay, do you think the properties of the flow will change if it is passing through a constant area duct, assuming it to be a steady flow, and assuming if I don't add any heat or if I don't do any work on this duct, do you expect any property of the flow will change? No, right? So basically the flow is going to retain all its properties, right? So let's say the flow enters with certain properties like P1, which is the static pressure at the inlet, static temperature at the inlet, static density at the inlet. It is going to be the same at everywhere throughout the duct. So you take any station on this duct, the properties are going to be the same. Okay, so this is a constant area duct which is not going to allow any property to change. Okay, but this is again, this comes with its own assumptions. Okay, because in reality no duct can be like that which does not change the flow properties. You will at least have some friction, right, which is going to change some of the flow properties. Okay, that also we will cover. We will come to something known as Fano flow, where we will deal with flow through ducts with friction. Okay, all right. Now, on the contrary, what happens if my duct is something like a variable area duct? So let's say the shape of my duct is changing. If the shape of my duct is changing. Now, if a flow enters this duct, do you expect the properties of this flow to change as it passes through the duct? Yes. Yes. Obviously, right? We know that as the area is going to change, the flow has to adjust itself to allow the same mass flow rate to pass through. Okay, so we have basically something known as conservation of mass, right? The mass conservation principle, which is a very, very basic governing equation in fluid dynamics, which tells you that whatever mass enters through the inlet has to exit through the outlet. Okay, which means the total mass is conserved. If that is the case, you know that the area of the duct is changing from one location to the other, which means the other flow properties has to change according to the change in area to allow the same mass flow rate to pass through. Okay, so let's say here if the area is A1 and if here the area is A2, if the velocity here is V1 and if it is V2 here, then to allow the same mass flow rate for mass conservation, you know that the continuity equation is valid, right? And if it is a single inlet, single outlet system for a steady flow, I can write A1 V1 is equal to A2 V2, right? Basically, you are saying that the volumetric flow rate of the fluid is going to be constant, right? So, so is this correct? Is this correct form of continuity equation that I have written over here? All of you agree? Or is anything missing? Yes, very good, Santosh. Right. So, yes, thanks. So, density is missing. Right. So, this is correct provided my flow is incompressible. Okay. This is correct provided my flow is incompressible with constant density. But if it is not incompressible, then I have to account for the change in density as well. So, I have to include density. Okay. So if this is a steady flow, then I can say that the product of rho AV is going to be constant, which means the mass flow rate is going to be constant. Okay. So you can see if the mass flow rate has to be constant, the product of these three quantities has to be constant, which means these quantities, they change in themselves to give the same mass flow rate. So obviously, when a flow is passing through a variable area duct, we will expect some properties to change. Okay. And how it is going to change is going to depend on the shape of the duct. Okay. So let's explore this more. Okay. So now we will define something to make our analysis more simple. We will define something known as quasi 1D flow. Okay. So quasi one dimensional flow. What does this mean exactly? So let's assume you have a duct, you have a variable area duct where the area is changing. You have a flow from left to right, from inlet to outlet. You assume that it's assumption, okay? It may not happen in reality, but the reality will be, the problems in real will be very close to our assumptions. That is why we make such assumptions. So we assume that the flow properties are going to be only a function of x, which means pressure at this station, let's say P1, is going to be different from pressure at this station P2. Okay, but at this particular station, if you look at this cross section of the duct, I will find that the pressure is same everywhere here. Okay? The pressure is going to be same everywhere. So the pressure does not vary with y, or it does not vary with the radius of the duct. So there is no internal variation. It is only the variation along the length. Okay. So I can say that there is only dou by dou x here, whereas dou by dou r is going to be, so this is not going to be 0 and dou by dou r is going to be 0, which means there is no radial change in the properties or there is no lateral change in the properties. It is only changing with x. Okay. So I can say if I take any station in the duct, the flow is going to be uniform. What do you mean by uniform? Uniform means flow properties does not change with space, right? It has a space independency. So if I take any station and at the length of this duct, I will find a uniform flow. Okay. So such an assumption where all my flow properties, area, velocity, pressure, density, temperature, stagnation pressure, entropy, whatever property you take, they're all going to be a function of x, only x, provided the flow is steady. If the flow is unsteady, okay, if the flow is steady, the properties are only a function of x. If the flow is unsteady, it is going to be a function of what? If it is unsteady, it is going to be a function of space and time both, right? Very good. So if it is unsteady, it's going to be a function of both space and time, because you know unsteady flows can fluctuate, so you can have temporal variation as well. Okay, so remember that for a quasi 1D flow, only these are the variations. Okay, now what are the governing equations that govern this flow? We have three basic governing equations. We have mass conservation, which says that the mass flow rate is constant. So rho u a, or you know, we use different notations. Sometimes we use u for velocity or v for velocity, but once we fix a notation, we will use it throughout. Okay, we have momentum balance, right? This is a 1D momentum balance. So basically your pressure forces and the inertial forces are balanced. Okay, so it says that it is basically the Newton's second law, right? The rate of change in momentum is equal to the net force applied. And what is the force here? You have the pressure force, you have the body force, or you have any other force that is acting on surface or on the volume. So it's basically force is equal to change in momentum. And we have the energy equation, which says that the total energy always remains conserved. Okay, so it is h1 plus u squared by 2 is constant, which means the h is the enthalpy here. Okay, it is the enthalpy, uh, which can be written as Cp into T. Okay, Cp into static temperature. And this whole term is known as stagnation term. We will define what is stagnation property and all when we go through the course. But for now, just remember this can be called as a stagnation. This can be collectively called as a stagnation term. Okay, so I can call this as H naught 2. Okay, or I can relate, or I can alternatively say H naught is equal to constant. Stagnation enthalpy is constant. This is writing energy equation in different way. So you will see that in this course, we are going to write energy equation in so many different ways, the way we want to get some results. Okay, but all of them mean the same. Okay, all right. Now, if the flow is going to pass through a duct, let's say the area of the duct is going to change. So we know that for the mass flow rate to remain the same, the properties has to change. Okay. Now, when the properties change, let's look at the area velocity relation, which tells you that if the area of the duct changes, how does the velocity in the duct will change? Okay. So we start with, so you take a duct flow, you can take any duct. So let's assume the flow, this is the inflow and this is outflow. So you can write, this is another way of writing the mass conservation equation. Okay, so you know that rho u a is equal to constant. You can just differentiate it on both the sides. You will get d of rho u a is 0. If you expand it using chain rule, you can write it as d rho by rho plus du by u plus dA by A is equal to 0. Okay, so this is another way of writing the mass conservation. Okay, now if you just do a simple manipulation, algebraic manipulation, okay, you convert dA by A and d rho by rho into the known properties like Mach number and all. So you try to relate, you will get an equation like this, which is known as the area velocity relation. Okay, so what does this formula or what does this relation tell you? It tells you that how does your area, dA by A is the change in area, or the fractional change in area, how does it relate to the change in velocity? And it depends on what? It depends on something known as Mach number of the flow. Okay, now we know that the flow could be of different regimes, right? It could be a subsonic flow, it could be a supersonic flow, it could be a hypersonic flow, or it could be a transonic flow, right? Now, let's see what happens when the flow is subsonic. When the flow is subsonic, what is going to happen, guys? For a subsonic flow, your Mach number is going to be less than 1, right? Mach number is less than 1. So if the Mach number is less than 1, you see that what happens to the sign of this term, m squared minus 1? Is it going to be positive or negative? M square minus 1 is going to be positive or negative? It's going to be negative, right? So this term is going to be negative, which means I can write this as dA by A is equal to minus 1 minus m squared times du by u. Okay. So let's say my flow is totally subsonic in the duct. Then my m is going to be a subsonic value. So this 1 minus m squared is going to be some constant value. Okay, so let's forget about it, whatever that value is. But what does this equation tell you? This equation tells you that for a subsonic flow, the area and velocity are going to be reverse. For example, if the area increases, the velocity reduces, or vice versa. If the area decreases, velocity increases. So they're kind of ulta to each other. Okay. So that is a variation for a subsonic flow. So you can see here, if this is a subsonic flow that is entering the duct, okay, and you can see that the area is decreasing, right? Because the area is decreasing, according to this relation, the velocity has to increase. So you can see the velocity is increasing, okay? And because the velocity increases, let's say at the inlet it is Mach 1, at the outlet it is going to be Mach 2. So M2 is going to be greater than M1. Okay. And if a subsonic flow enters a divergent duct, you will see that the velocity is going to decrease because the area increases. So if this is your M1 and this is your M2, M2 is going to be less than M1. So now, based on this, can you guys tell me whether the converging duct acts as a nozzle or the divergent duct acts as a nozzle? Which one is a nozzle out of them? So nozzle is something that accelerates the flow. So which one is a nozzle? It's a convergent duct, right? And we know this. We know this already because we are more comfortable with incompressible flows. And incompressible flow, we have the Bernoulli's equation, continuity equation. All that tells us that area increases, velocity decreases, pressure increases, right? So we know. And similarly, the divergent duct is going to be the diffuser. So diffuser is something which is going to slow down your flow. Okay. Now tell me what happens if the flow is supersonic. If the flow is supersonic, my Mach number is going to be greater than 1. If the Mach number is greater than 1, this term m squared minus 1 is going to be positive, right? So if this is positive, then my dA by A is going to be m squared minus 1 times du by u. So this is going to be a positive quantity, which means my dA by A and du by u are going to agree with each other, which means they are in direct relation, right? Which means if the area increases, velocity increases, area decreases, velocity decreases, and vice versa. Okay, this is what happens in a supersonic flow. So you can see here, so this is a converging duct. If a supersonic flow enters the converging duct, what do you expect? The Mach number is further going to increase. At that exit, you are going to have a M2 which is greater than M1. If it is a divergent duct, a supersonic flow enters a divergent duct with M1, the Mach number is going to decrease because the area decreases. At the inlet, it is going to be M2, which is less than M1. So now can you tell me which one acts as a nozzle? Whether convergent duct acts as a nozzle or divergent duct acts as a nozzle for a supersonic flow? Which one acts as a nozzle? Is it divergent duct? It is convergent duct again, right? You can see the Mach number is increasing. So it's a convergent duct that acts as a nozzle. Okay. So, but the difference here is, look at the shape of the duct. Okay. So when the area increases, the supersonic flow is going to accelerate. And the area decreases, supersonic flow is going to decelerate, which is in complete contrast to subsonic flow. Okay. So this is what happens when the flow properties change. The flow changes from subsonic to supersonic. Things are going to change dramatically. Okay. So these things happen. Now, the story does not end here. Okay. The story does not end here. Why does the story not end here? Because it is not just the variation in velocity or Mach number. The other flow properties also change. They change in more unexpected fashion than how they change in a subsonic flow. Okay. So we know for a subsonic flow or for an incompressible flow, I would say, remember that, guys, when I say subsonic flow, it could be both incompressible or compressible. So what is that Mach number which demarcates subsonic, compressible and compressible flow? 0.3. Very good, Santosh, right? So it's 0.3. That is the Mach number. You would say above 0.3, we will consider the flow to be compressible, and below 0.3, you can treat that as incompressible. Okay. And why is that 0.3? Why is that exact number 0.3? Why is it not 0.4 or 0.5? We will see. We will see in the course. Okay. So now come back here. What I was telling you is, it is not only the variation in Mach number, even the flow properties like pressure, density, temperature, entropy, these properties can also change. And the entire subject becomes very interesting. Entire subject becomes very interesting because these flow properties change. Okay. And it is going to give you amazing results. Okay. Yes. So there's a doubt, for a supersonic flow, the nozzle is divergent. Yes. So you can see that a diverging duct increases the velocity, right? So that is going to be a nozzle. So nozzle is the one which increases the velocity, which accelerates the flow. So diverging duct is going to be a nozzle. Converging duct is going to be diffuser. That is why I said it is in contrast to a subsonic flow, right? Okay. Yes, Himagna. So left one is divergent. Yes. So the divergent duct will act as a nozzle, right? It is going to accelerate. Is that fine? All right. Okay. So yes, now if this is clear to you guys, if you guys understood this, you help me with a small exercise, which I will show you in the next slide, where we will see how does the properties of these flow change. Okay. How does the properties of these flow change? So yes. Yeah, before that, tell me what happens when the flow is going to be sonic, or when the flow is exactly where the Mach number is equal to 1. So if you put Mach 1 here in the equation, what are you going to get? You are going to get dA by A is equal to 0. Okay, which means dA is 0. The change in area is 0. If the change in area is 0, so it's like when you differentiate a quantity, you get it as 0. What does that mean? It means there is either maxima at that point or minima at that point, right? So it's the optimum condition where the derivative becomes 0, right? So here I can have two possibilities, whether my area is going to be maximum or my area is going to be minimum when Mach number is exactly equal to 1. So which possibility do you think is a physically possible or a feasible solution? Whether at Mach 1 the area should be minimum or whether it should be maximum. It should be minimum, right? That is the only physical possibility, because if you go for maximum case, then you don't know how much maximum your area can be. It could be infinity, right? So that is something not very physically possible. Okay. So minimum condition is a physically possible one. So we will say that the flow is going to accelerate in subsonic, the flow is going to a subsonic flow is going to accelerate in a converging duct. It can maximum go to sonic flow. So if the Mach number is less than 1 at the inlet, at the outlet, it can be maximum Mach 1, not more than that, because that is where I get dA is equal to 0. And then if my supersonic flow is slowed down to a subsonic flow, it can maximum go to Mach 1. It cannot further slow down. Okay. So you always have this limit dA tends to 0 where the area becomes minimum. Okay. All right. So if this is clear, so you guys now help me with this. Now let's see how does the flow properties change. Okay. How does the flow properties change when we have uh, the variation in area in the duct and the flow is taking place. So I have listed down few flow properties like velocity, pressure, temperature. Okay. We will take different cases and we will see how does the property change in each case. So let's take the first case. Okay. Our first case is a converging duct. Okay. It is a converging duct. Let's say you have a subsonic flow here. So Mach number M1 is less than 1. Okay. If I have a subsonic flow here at the inlet, tell me what happens to the velocity in the duct? What happens to the velocity? Increases. Very good, Nandini. Very good. So velocity increases. What happens to static pressure? Static pressure is going to decrease. Very good. Because we know that, so see, whenever you deal with a compressible flow, there is always an interplay between kinetic energy and internal energy. Okay, we will see that both kinetic energy and internal energy are themselves related through Mach number. Okay, so if the internal energy increases, kinetic energy decreases and vice versa. Okay, so static pressure is going to decrease because when flow expands, pressure always drops. Okay, it's a favorable pressure gradient. What happens to static temperature? Temperature is going to decrease because our internal energy decreases. And what happens to density? Because your pressure and temperature are both decreasing, density is going to decrease according to ideal gas law, P is equal to rho RT, right? What happens to enthalpy? What is enthalpy? Enthalpy is Cp times temperature, where Cp is constant for a calorically perfect gas. So the enthalpy is also going to decrease. What happens to stagnation properties? So stagnation properties are like stagnation temperature, stagnation pressure. Very good. They're going to be constant because see, stagnation properties can only change when there is some irreversibility in the system or if there is some heat transfer taking place in the system. If all that is not there, then you assume the flow to be isentropic and stagnation property will be constant. Okay. What happens to entropy? What happens to entropy? Yes. Is it going to be the same or will it increase? Yes, it's going to be the same, right? Because we assume the flow is isentropic. Okay, if it is isentropic, the entropy is going to be constant. Okay, so this is the first case. Now let's go to the second case where you have a diverging duct And let's again say you have a subsonic flow at the inlet. So because it's a diverging duct, it acts as a diffuser where velocity drops, Mach number drops, static pressure increases, static temperature increases, density increases, enthalpy is going to increase, stagnation pressure is going to be constant, and entropy is going to be constant. Okay. And let's go to the next case where I have a converging duct. Now, the oncoming flow is a supersonic flow where Mach number is greater than 1. Okay. So, this acts as a diffuser or nozzle? Acts as a diffuser or nozzle? Diffuser, right? Because it's going to slow down the flow. It is not accelerating, right? Okay. Now, who can unmute and tell me all these properties for this case? Anyone? Please feel free. Anyone? Can anyone volunteer? Yes? Nobody? Dheeraj, you would like to attempt? All right, so anyone can answer. What happens to velocity? What happens to Mach number inside the diffuser? Is going to decrease, right? Static pressure is going to increase, static temperature is going to increase, density is going to increase, enthalpy is going to increase, and just like the other cases, stagnation properties and entropy is going to be constant. Okay, very good, Dheeraj. Thank you. Now, the last case, consider again a diverging duct, but the oncoming flow is supersonic. So it acts as a nozzle, right? So what happens here? Because it acts as a nozzle, it is going to accelerate, increases, pressure drops, temperature drops, density drops, enthalpy also drops because static temperature decreases. And again, these properties are going to be constant. Okay. Now, guys, remember the entropy need not be constant always. If I tell you that the process is not isentropic, the other property variation would still be like this, but the entropy can still increase. Okay, because for a always for a possible process, entropy increases. Okay, entropy never decreases. That is from the second law of thermodynamics. Sorry, the third law of second law of thermodynamics, right? Which says the total entropy is always constant. Okay, so yeah. So now I hope you understood the how does the properties change in a duct. Okay, now let's go to something very interesting, which is our concern. Now we have learned about subsonic flow and a supersonic flow. How does this flow take place inside a duct? Now you answer this question. How will you accelerate a subsonic flow to a supersonic flow through a single duct? You know that you can accelerate a subsonic flow, but if you pass it through a converging duct, it can maximum go to sonic. It cannot become supersonic. Similarly, if you decelerate a supersonic flow, it can maximum go to sonic. It cannot become subsonic. But if I want to do that in a single duct, what is the shape of the duct I should be using? Yes, I should be using a convergent divergent duct, right? Or a convergent divergent nozzle. Why is it called a nozzle? Because it accelerates subsonic flow to a supersonic flow. The Mach number increases throughout, right? So you can see here, it is a convergent divergent nozzle. CD nozzle is what we call it in short. So you can see the shape of the nozzle is like it converges first, the area decreases, then the area becomes the minimum. This is where exactly your dA becomes equal to 0. Okay. Because it is a minimum area point, what is going to be the Mach number here? What is the Mach number? Very good. It is going to be 1. And if the Mach number is 1, that is a very critical point, right? Because your flow is shifting from one regime to other regime, and it is becoming 1. Okay. So this is a minimum area point. This is known as throat. Okay. What is this known as? It is known as throat. Throat is the minimum area point in the nozzle. Okay. This is where the Mach number becomes 1. Now, guys, remember your dA by dA is equal to 0. Okay. dA is equal to 0 means that your area is minimum, and that is called as throat. Okay. Sometimes people represent this throat with a star. Okay. We represent it with a star. What does star mean? Star means you are at Mach is equal to 1 condition. Okay. But this is not always true. A throat need not always have Mach 1. So a throat could also have a subsonic value of Mach number, and it could still be a throat. So a general notation is that we will use a subscript of T. Let's say if I want to refer to area at the throat, I will say AT, which means area at the throat. So this is when the Mach number at the throat is equal to 1 or less than 1. Okay. And if the Mach number is exactly equal to 1, you will call that as A star. So star always represents when the Mach number is exactly equal to 1. Okay. These are just about notations. I want you guys to take a note of it. Okay. So you need a convergent divergent nozzle. The flow is going to accelerate from subsonic to sonic at the throat. From sonic, it is going to accelerate to supersonic in the divergent section, which is a nozzle for a supersonic flow. So the entire thing combined is known as convergent divergent nozzle. Okay. Why is this important? Why are we learning this in gas dynamics? Because you would have seen, what is this, guys? What do you see in the picture shown here? This is so you see a bell-shaped object, right? What is it? Very good, Dheeraj. Yes, it is a rocket nozzle, right? So you see a rocket engine, so which expands the exhaust. The rocket exhaust is expanded through a CD nozzle, so to accelerate the flow from subsonic to supersonic. Right, that is why your nozzle or the rocket is propelled in supersonic speeds or hypersonic speeds. Okay, so you see such structures here, right? So to expand any flow to supersonic speeds, you need such kind of variable area duct, which is a convergent divergent nozzle. So you see this rocket engine, the schematic of rocket engine here. Okay, so you have the combustion chamber, also known as a thrust chamber, where fuel and oxidizer is mixed. It is ignited, where the chemical energy is converted into heat energy. Okay, and then the flow is accelerated through a CD nozzle, where it expands to supersonic flow, and it is going to give the thrust to the nozzle in the reverse direction, which propels your nozzle. Okay, so that is why. So this is not the only application of a CD nozzle. You have other applications as well. For example, supersonic wind tunnel. So have you guys seen supersonic wind tunnel? Anyone? You would have seen in your colleges if you have. Yeah. So how does it look like? Is it different from a subsonic wind tunnel, low speed wind tunnel? It is different, right? The construction wise itself, it is different. So how does it look like? You have a reservoir. You have a container where the gas is stored at a very high pressure and temperature, which is known as reservoir, where the flow can be assumed to be in stagnation condition, and then it is expanded to a supersonic flow using a throat, using a nozzle, which is a CD nozzle, where the at the throat you have Mach 1. Okay. And then once you get a supersonic flow at the exit of the nozzle, you have a constant area duct, which is known as a test section, where the models are placed and it is tested. So you have a supersonic flow in the test section. Okay. And because you cannot dump the supersonic flow directly to the atmosphere, you have to slow it down to subsonic speed. So what do? Again, you use a CD nozzle. Now here, because it slows down the flow from supersonic to subsonic, you call it as a CD diffuser. Okay. So this is a CD diffuser. This is a CD nozzle. Okay. So this is a setup of a supersonic wind tunnel. So here also we will be using CD nozzle. Okay. So this is where the importance of CD nozzle comes, and the application is very diverse. Okay. All right. So now let's learn some more interesting things about CD nozzle. Let's see how does a flow takes place across a CD nozzle. Let's take a nozzle, convergent divergent nozzle. You have a flow from inlet to outlet. This is subsonic flow. It becomes Mach 1 sonic at the throat, and it becomes supersonic at the exit. Okay, at the exit of the nozzle. Now, if I consider an isentropic flow, an isentropic flow means there is no irreversibilities, there's no heat transfer. It is simple isentropic flow, which follows isentropic relation. Okay, so you can derive a relation between the area ratio and the Mach number. Okay, area ratio and the Mach number. So what is A by A star? A is the area at any given location in the nozzle. A star is the throat area. So we always normalize the area. We always normalize the area to the throat area. This is a normalized area. And you can see for a supersonic flow through a CD nozzle, this A by A star, sorry, not for a supersonic flow, for isentropic flow, this A by A star is a function of Mach number and gamma. What is gamma? Gamma is a specific heat ratio, Cp by Cv, which is constant for a gas, calorically perfect gas. So A by A star is a function of Mach number. So if we just plot A by A star versus Mach number, don't worry, we will derive this relation, okay, in the class. For now, I'm just showing it to you. So you will see that for a given value of A by A star, you have two values of Mach number. One value corresponds to, so you have two values. One value corresponds to subsonic flow and the other value corresponds to supersonic flow, which you can see here also, right? So let's say this station and this station has the same A by A star, but here the flow is subsonic and here the flow is supersonic. Okay, so you will have two solutions. Okay, one is subsonic and the other is supersonic. So, and when the A by A star is exactly equal to 1, where A is equal to A star, the Mach number is going to be equal to 1, which is the sonic flow or the throat condition. Okay. So this is about how you relate the geometry of the CD nozzle to the flow Mach number. Okay. Now, if you look at your gas tables, you will see that they have tabulated the values of A by A star against different values of Mach number. Okay, so you can directly look the values there. You need not remember this relation. Okay, even for exam, you need not remember. This will either be given to you or you can look it up in the gas tables. Okay, all right. Now, let's consider a CD nozzle where the flow is going to be isentropic. So I have a CD nozzle like this. Okay, the incoming flow is going to be subsonic. The flow is barely sonic at the throat. So Mach is 1. So this is the star, right? A star. And at the exit, the flow is going to be supersonic. Okay. Now, if I have a nozzle, the design of the nozzle is fixed, right? Which means, let's say the area at the exit is AE. Area at the exit is AE and the area at the throat is A star. So my AE by A star is fixed. Because the geometry of the nozzle is fixed, I know what is my A by A star. Because I know my AE by A star, I can get the corresponding value of Mach number at the exit using the last relation. Yes. Yes, guys, agreed? If I know my A by A star, I can get the value of exit Mach number from the area Mach relation, which I just showed you in the last slide. Right? Yeah, all right. So I know my exit Mach number. Let's say this exit Mach number corresponds, which value will you choose? Will you choose a supersonic value or subsonic value?
Yeah,
You will obviously choose a
will it
supersonic
take
value.
some time?
I think so. Yeah, sir. 10 more minutes.
Yeah, no problem. You can continue. Okay. Yeah.
Okay.
Thank you.
Thank you. So you will choose a supersonic value of Mach number at the exit. Okay. Now, because my ME is now fixed, and if I have a isentropic flow throughout the nozzle, you can use isentropic relations and you will know what is your PE by P naught, which is a function of Mach number, right? That is the ratio of static pressure at the exit to the stagnation pressure. Because it is isentropic flow, my stagnation pressure is going to be constant. Okay. So, because my ME is fixed, the ratio of P by P naught is fixed. Okay. The ratio of P by P naught is fixed. And how is P by P naught given? Or P naught by P? It's easier to find P naught by P. So let's write it as P naught by P. So P naught by P is given by 1 plus gamma minus 1 by 2 ME squared power gamma by gamma minus 1. Right? So if I know my ME, I know my P naught by P. Now what is P naught? P naught is a stagnation temperature, which is the stagnation pressure, which is the pressure in the reservoir. Now the reservoir conditions are always fixed. So my P naught is kind of fixed. Unless I change it, my P naught is always fixed. Okay. So I know my P naught. So everything in the flow is fixed except for PE. So the controlling factor that I have in my hand is PE, which is a static pressure at the nozzle exit. Okay. Which means if I want to have an isentropic flow through the nozzle, my P naught by PE ratio, the pressure ratio, which is P naught by PE, should correspond to the Mach number, which is dictated by A by A star. So to have an isentropic flow through the nozzle, there is one and only one solution. So there is a unique solution for a supersonic flow. Okay. There is a unique solution for a supersonic flow. Okay. Which is given by A by A star and the Mach number at the exit. Okay. They dictate the solution. Okay. This is when my throat is choked. Now, if my throat is not choked, then do you think we will have supersonic flow at the exit? Will we have supersonic flow at the exit? No, right? The flow is going to be subsonic because you are not going to reach the appropriate pressure ratio. Okay. So to get so if my throat is choked, then my P naught by P star is going to be some value, right? Which is you put Mach number is equal to 1 here. If you put Mach number is equal to 1, it is going to give you 1 plus gamma minus 1 by 2 power gamma by gamma minus 1. So you can take gamma is equal to 1.4 for air. You will get P star by P naught is equal to 0.528. Okay. So if my ratio is not this, then I'm not going to get choked flow in the nozzle or sonic flow in the nozzle. Okay. If my ratio is not this, I'm also not going to get the supersonic flow at the exit. So for isentropic supersonic flow at the exit, the pressure ratio should be such that the flow is sonic at the throat, which means the P star by P naught should be 0.5 to 8, and the exit pressure ratio should be such that it is dictated by the area ratio and the exit Mach number. Okay, so this is about the isentropic flow in the across the nozzle. Okay, yeah, I know because it's first time it might be too much for you guys. We will do these things slowly. We'll understand it. Okay, in the regular classes, but because it's a demo lecture, I just wanted to, give you guys a flavor of what it means by a CD nozzle. Okay, so yeah, at least did you guys understand something about this? Yeah. At least some things are clear. What is a CD nozzle? What does it do? How does it accelerate the flow? How does it decelerate the flow? What do you mean by pressure ratio? What is throat? At least these things are clear. Okay, great. So this is about isentropic flow. Now you can also have non-isentropic flow. That is, when the pressure ratio is such that the flow is not isentropic, or when the exit pressure is not conforming according to the design Mach number, then you are going to have some drama in the nozzle. What is that drama? You're going to have shocks. The shock is going to move. It can be in the divergent section. It can be in the exit. You will have oblique shock. You will have expansion waves. Okay. Then we will, the nozzle is going to behave in a very weird way. Okay. So we will see all that. Okay. Not now, but later on. Okay. So yes, this is how the properties vary. So you see that the Mach number increases from 0 to 1, which is at the throat, and then it goes to supersonic value at the divergent section. Similarly, static pressure reduces, it reaches 0.5 to 8, the pressure ratio at the throat, and then it drops to the isentropic value at the exit. Similarly, for the static temperature. Okay, so this is how properties vary. So this is about a flow through CD nozzle for isentropic case. So yeah, that's all I wanted to tell you guys. Now we also have other flows, non-isentropic flows. We'll see that later. So before we close, let's try to solve. Yeah, so you would have seen this type of structures, right? At the exhaust of nozzle or at the exhaust of some fighter jets. What is it? Can anyone say? What are these structures? Shock diamonds, very good, right? These are shock diamonds. So basically you have shocks and expansion waves colliding with each other, and they form shock diamonds. They are very beautiful structures found in the exhaust of rocket jets or fighter jets. Okay, we will see why does shock diamonds occur and what is its relevance. Okay, so before that, let's look at a gate question. So this question is from 2023, GATE 2023. Let's read this question. A perfect gas is stored in a large reservoir exhaust. It exhausts into the atmosphere through a convergent duct. So you have a reservoir. It is connected through a convergent nozzle. Convergent nozzle. So this nozzle is going to exhaust the flow. The reservoir pressure and temperature is P0 T0. Jet emerges from the nozzle at choked condition, which means the exhaust jet is going to be choked. The Mach number at the exit is going to be equal to 1. Okay. And because it is choked, can I call the conditions over here its star conditions? Yeah. So it is going to be the Mach number is 1. Pressure is going to be P star. Temperature is T star. Density is rho star. Okay. If the reservoir pressure is increased, if my P0 is increased, what happens? Would someone like to guess what happens? So now the nozzle is choked. Okay. So the exhaust flow is at Mach 1. if I increase the reservoir pressure, do you think the nozzle is going to be still choked or will it become unchoked? What do you think? Will the nozzle still remain choked? Very good, Shannon. So it is going to remain choked because the temperature ratio is not changing. You are only increasing the pressure in the reservoir. So T naught is still the same. T star is still the same. So your T star by T naught is the same even after increasing P naught. So because this is same, the nozzle is still going to be choked. Because the nozzle is choked, the P star by P naught ratio has to remain the same, which is 0.528. Okay. If this has to remain the same, and if I'm increasing my P naught, my P star has to increase, which means the exit pressure has to increase. The exit pressure has to increase. The exit temperature is constant. So, according to ideal gas law, exit density has to increase, right? And because the exit Mach number is 1, okay, and temperature is constant, the exit velocity is going to be constant, which is given by so exit velocity is given by Mach number into root gamma RT, right? So what is the answer? Your pressure and density is going to increase, but the other properties will remain the same. So option C is the answer. Okay. So this was asked in GATE 2023. Yeah, don't worry. For now, you guys have just understood, so it will take time to absorb these concepts slowly. For now, just wanted to. What if T also increases? So if the exit static temperature increases or if it changes, then it will depend on how much it increases. So if this ratio T star by T naught, if it changes, then the nozzle will become unchoked. Okay. As long as this ratio remains constant, it is going to be choked. So if your temperature increases to change this ratio, it is going to be unchoked. If it is unchoked, then all the other properties will also change. Okay. All right. So that's all, guys, for now. Yes. I hope this session guys have any doubts. Please talk. Any was a